Welcome, everybody. My name is Lorenzo Capra. I am from the University of Milan. My talk is about a natural model for reconfigurable distributed systems based on Petri Nets and rewriting logic. Let me start presenting an outline of this presentation. I'm going to give some motivation and goals. Then I will overview the modeling frameworks. I will present some application examples. I'm going to discuss about some perspectives, in particular some ongoing work and some open issues. So let me start by giving some motivations. Formal models for distributed systems are very important. And dynamic reconfiguration is an uncovered issue, or by most formalism. Dynamic reconfiguration is a key issue, is why the class of distributed system, for example, automated systems, self-adapted systems, reactive systems, dynamic networks, social networks, and so on. So there is a need for well-supported and easy to use formal models, able to cover reconfiguration aspects. Here is a list, a non-exhaustive list of well-known formal models for distributed systems, graph transformation systems, classical Petri Nets and process algebra, and some extensions of Petri Nets and process algebras aimed to cover reconfigurability issues. All of these formalism have some drawbacks. Graph transformation systems are not adequately supported by tools, and they usually adopt a rigorous but too restrictive style for transformation tools. Classical Petri Nets and process algebras cover mobility more than structural changes. And finally, Petri Nets and process algebra extensions. Let me mention in particular an extension of Petri Nets called Nets within Nets, in which tokens that flow through the places of a net are internets. These extensions are interesting, but unfortunately are still weakly supported. In addition, they are richly annotated and difficult to use by non-expert users. The preliminary proposal of this work is an efficient implementation based on mode of rewritable place transition systems. Place transition systems are a well-known class of Petri Nets. And mode is a very expressive and highly performing declarative language based on semantics, on an intuitive semantics based on rewriting. In particular, the semantics of mode is expressed by rewriting logic. Mode is often used as a meta language. In some sense, it may be used as a logical framework to describe other logics, other formalism, other languages. On their side, Petri Nets are a reference model for any formalism that wants to describe concurrent or distributed systems. For several reasons, because Petri Nets are provided with an intuitive distributed state notion called the marking. There is a wide spectrum of model analysis and validation techniques. And finally, Petri Nets are well supported by automated tools. And the idea of using mode, or at least rewriting logic to encode Petri Nets is not new. Let me just mention a pioneering work by Mesege and others, which dates back around 20 years ago. There is also a class of Petri Nets called reconfigurable Petri Nets, defined by Padberg and others a few years ago, which is a family of models in which Petri Nets are combined with rewrite rules, expressed using the classical rule style of graph transformation systems, that is by double push-outs. A push-out is a pair of morphism. There is also a formalization of mode defined for model checking purposes by Padberg and Schultz, but this formalization, this mode formalization is actually very inefficient. So the drawbacks are inefficiency, rules difficult to write and check, and a reduced flexibility. So the novelty of my proposal is an efficient implementation which fosters user-definable rules, structural extension. For example, it should be easy to add features such as transition priorities, marking-dependent hedges, and so on. User abstractions to deal with scalability and so forth. Let me present an overview of the frameworks. Petri Nets are bipartite graphs formally expressed by a five tuple n composed of P and T. P and T are two sets representing the nodes of the graph, places and transition respectively. Places represent the system state variables. Transition represent events that may locally change a state of the system. Edge connections are represented by three kinds of maps, input, output, and inhibitor. Each of these maps associate each transition to a multiset on the set of places. It means that edges may have a weight, okay? The input and output connection for each transition must be different because each transition must actually represent a state change. The notion of marking that represent a distributed state is simply expressed once again by a multiset defined over the set of places, and the transition is enabled in a given state if and only if this condition holds. These conditions involves input hedges, which expresses the number of tokens that must be present in a given state, and inhibitor hedges that represent, on the contrary, the upper bounds of tokens in the places of a net. A transition that may fire, a transition which is enabled may fire, leading to a new state. The new state is defined from the old state using the O and I connection, the input and output connections. All these operators, relational operators, and plus and minus operators are multi-set operators. Finally, PT system is just a pair composed of a net and an initial marking. The interleaving semantics of a system is a state transition system called reachability graph, in which nodes represent reachable states, whereas edges represent direct state transitions. And what is interesting is that PT nets enriched with inhibitor arcs are a Turing powerful model. Here is an example of two place transition systems. This system represents two configurations of very simple manufacturing systems in which there are two production lines. The two production lines work in a symmetric way. They work some raw pieces that are loaded into the system. Each pair of worked pieces is then assembled to get the final artifact. This system is fault tolerant in the sense that after a fault that may occur on either line, the system layout changes in order to allow the system to continue working in a degraded way. There is a reconfiguration steps from the nominal behavior to the faulty behavior, and there is also a back reconfiguration after an overall repair of the system. The process and repair steps are only described in a very abstract way in this model. One of the critical issues is that semi-worked pieces on the faulty line have to be moved on the available line in order for a production cycle to be correctly completed. In other words, the system reconfigurations may only take place in safe conditions, which ensure that the system do not enter a deadlock. Also, this simple model cannot be easily described using Petri Nets, even if Petri Nets with inhibitor hacks are Turing powerful. And we are only able to specify the initial and final stages of the reconfiguration, but we cannot describe the transformation process unless we enormously complicate the model. A solution may be provided by reconfigurable Petri Nets defined by Pabder and others, but the problem is that the use of graph transformation systems rules poses serious limits in the applicability of this model. And I've used mode to re-implement an extensible class of a rewritable PT system. The middle term A is to develop a hybrid formal modeling framework for dynamic systems, which is accessible by non-expert users and expressive enough to specify quite complex evolutionary strategies. By the way, this is just a preliminary step of this work. Let me provide a few hints on mode. Mode as a declarative language with a very intuitive writing semantics. The statements of mode are equations or rules. Equations and rules have the same syntax in some sense. They are composed of two sides, and both the left and the right sides are terms defined of a given signature. These terms may contain some variables. There is also a third kind of statement that is membership clauses. The syntax of a membership clause is this one. The left-hand side is a term and the right side is a sort. Equations represent simplification rules. Instead, rewriting rules represent concurrent computations. Mode is provided by lots of advanced features, for example, a pattern matching module operator equation attributes, a mix fix, a user-definable operator syntax, user-definable evaluation strategy, subsorting, that is subtyping, and partiality, generic programming, reflection, and meta levels. And formally, a mode program is a logical theory where computations are logical deductions. Syntactically, a mode program is composed of functional modules and system modules. Functional modules specify an equational theories. An equational theory is a pair composed by a signature and a set of axioms. The signature is composed of kinds, sorts, subsorts, and operators. Kinds are, in some sense, implicit equivalent classes defined by the subsort relations. So a kind is the union of sorts related by the subtyping relation. The set E of axioms is composed of equations and operator equational attributes, for example, associativity, commutativity, idempotence, and so on. Sorry. The model of a mode specification is an algebra, and the best model is the initial algebra. The initial algebra is an algebra which is both junk and confusion-free. The initial algebra may be mathematically expressed by the quotient of the term algebra, T sigma, where the equivalence classes that represent the elements of the initial algebra, all the terms that prove to be equal using the axioms of the specifications. And if the axioms are Church-Rosser and terminating modulo the axioms, then this nice property holds. This nice property guarantees that the denotational and the operational semantics of a mode specification, of a well-formed mode specification, coincide, and this is expressed by an isomorphism between the initial algebra and the algebra formed by the canonical terms. The canonical terms are the final terms of a rewriting process. A system modules formally specify a generalized rewrite theory. A rewrite theory is essentially a membership equational theory which specifies the algebraic structure of the system. More a set of rules expressed by set R. There is also a map phi of frozen operator arguments. Let me skip this part because the frozen arguments are not used in my specifications. So essentially, a system module is just a rewrite theory with, in addition, a set of rewrite rules. And the initial model of a rewrite theory is expressed in terms of state transition systems or categories. The idea is that for each kind key, there is a state transition system defined in this way. The states of this transition system are the equivalence classes corresponding to the element of the initial algebra. And the state transitions corresponds to equivalent classes of rewrites modulo the equational theory of proof equivalence, which is associated to a given rewrite theory. The idea is that different transitions corresponds to different true concurrent computations that may be done on a system. If the ground coherence property holds between rules and equation, this property is syntactically checkable. Completeness is ensured. It means that any rewrite of a term T with any rule of set R is also possible if we consider the canonical form of T. And this property is used to implement the rewrite mechanism in a very efficient way. Let me start speaking about the implementation the mode implementation of Rewriting Petri Nets, it is essentially based on two generic modules, bag and map. Okay, these modules are parameterized. For example, a bag P term, where bag P represents a bag over the set of places, which is the building block of the mode specification of Rewriting Petri Net. This bag P term is expressed by a weighted associative sum. Here is an example. Notice that the sum symbol is not just a syntactical element, but it actually represents the multiset sum. The next element is a net term, a net term which describes the structure, the graph structure of a Petri system, is expressed in turn as a map from transition to triplets of bags, representing the input, output, and inhibitor connections respectively. Here is an example. And finally, there are system terms obtained by just juxtaposing a net and a bag. The bag represents the initial state. The mode implementation of Rewriting Petri Nets is built of a few mode modules, most of which are function modules, and only a few of them are system modules. For example, you can see here the module which specify a generic bag, and you can identify easily the operators that represent the sum, the difference, and the relational. All these operators are those used in the formal definition of Petri nets I presented at the beginning of this presentation. This second module is the module that represents a Petri system, and in particular, you can notice the fact that a Petri system is actually defined as a map between transition and local incident matrix, defined as triplet of bags. In particular, there is an enable predicate which checks the enabling condition of transition. And there is also a membership equation which is used to characterize a well-defined system. And another very important module is the generic module PT-EMU, described on the top of this slide. This module is a system module. It contains a rewriter rules labeled by firing, and this rewriter rule actually encodes the rewrite defining rule of a Petri net. You can observe that the syntax is very close to the formal definition. The idea is that any Petri net expressed in some XML format may be automatically translated in two different modules, one that describes the structure and initial state of the net, and another which contains the rewrite rules of our system. In this case, in this example, there are two rewrite rules that correspond to the two configurations I shown before. The interleaving semantics of a Rewriting Petri system is very easily defined by the set transition system that can be built from the term that represents the initial system. It is also possible to guarantee at static level that rewriter rules are correct, and this is obtained by rephrasing each rule in such a way that the obtained system belongs to the system sort. It is also possible to specify lower level rules, not only system level rules. And it is also possible to guarantee that a given rule is valid using a simple but powerful library of net operators. For example, the operator set W, which is defined in this module, sets a given arc weight. By using this operator, it is possible, for example, to introduce new nodes into our nets. By the way, it is possible to introduce new edges. It is also possible implicitly to remove nodes and so on. The idea is that if we use one such operators in our rules, we have the guarantee that the corresponding transformation is well defined. Some application examples. Using mode, we may conveniently use also some tools that come with the mode. For example, there is an efficient LTL model checker. In this slide, I just show the usage of the basic command, which is the search command. In the first example, I'm looking for final states in the overall system, and you can see that there are no solutions. It means that the overall system, that is the system composed of the initial configuration and its possible writings, is lives in some sense. There is another example. In this case, we look for these states inner to the possible single configurations of the systems. You see that in that case, the search commands provides a positive answer. That is, if we consider each configuration of the system in isolation, that is without reconfiguring it, the system may enter a deadlock state. It's also possible using exploiting the fact that our model is a hybrid model, that is, we can also use some analysis verification techniques typical of Petri nets. For example, we can compute semi-flows to check structural invariant properties. As an example, computing semi-flows on the set of places, we can formally guarantee that our model is structurally bounded. And this is very important because structural boundedness is a precondition for model checking. Let me shortly conclude my presentation by discussing some issues and some ongoing work. The first question is, how does this approach scale up? There are some possible answers. The first one is that, as for any graph transformation systems, we should reason about isomorphism. For that purpose, it is possible to define a canonical representative for each system term, so that two system terms are isomorphic if and only if their corresponding canonical representatives are. Below, it described the idea in terms of functional modules. There is a new operator, canonize, that takes a system and puts that system into a canonical form. Another interesting possibility is the use of obstruction by adding new equations or new rewrite rules. Abstractions may be also used to define some hierarchical views. for example, transition refinements, agglomeration, and so on. An interesting example of abstraction is that described below. The idea is that we may be interested only to inspect the evolution of the system, disregarding the internal behavior of each system, looking only at the possible structures that the system may reach. And once again, this may be achieved by using an equation to our specification. This equation allows us to aggregate different systems that share the same structure. Another interesting possibility is to use high-level Petri nets instead of low-level Petri nets to describe the base systems. For example, assume that we are interested in describing a whole bunch of systems like those described in the running example. This may be done using high-level Petri nets, for example, color Petri nets. And this model, for example, describes a bunch of flexible manufacturing systems like that described at the beginning of my presentation that synchronize at a given point. So the idea is to move towards rewritable high-level Petri nets. By the way, it is an interesting ongoing work, but it involves some advanced features like the meta-level of mode, the use of a unification Highlevel modules of mode, and so on. Some open issues. The rule-based model is simple, elegant, but it's difficult to use in the case we have to represent complex evolutionary strategies. That requires the use of modes, meta-level, or strategy modules. Another major concern is that the equations, much more than rules, may strongly affect the efficiency of any rewriting-based system. So that, for example, different, even if equivalent axioms may perform in a very different way. So the framework should take care at the most as possible of this issue, allowing the modeler to concentrate on the system specification in some sense. In conclusions, I presented the preliminary formalization of a hybrid, of an hybrid and hopefully easy to use modeling framework for dynamically reconfigurable distributed system based on mode and PT system. The approach takes advantage of the features of both formalism. The weakness is that PT nets, even if too powerful, are poorly expressive, and that rewriting efficiency is a major concern. For that, I planned some ongoing work, for example, the canonization of states, the use of rewrite strategies, and the extension of this approach to high-level Petri nets. Here is the GitHub repository in which the mode modules are stored. Some short bibliography, sorry. Thank you for the attention, and thanks to the reviewers for their valuable work.